vacuum technology. So be it the water pump that is being used to have the water in your tank, okay, from the bottom of the ground, you are using a pump there, okay. A vacuum cleaner that you usually use is a vacuum example of a vacuum technology, okay. So even if you are using a water pump which is actually like connected to, let's say, a 20-liter bottle, those pumps, manual pumps which are there, that also basically creates a vacuum. So what happens usually is that for example, you have the electrons, okay, and you want it to flow from, let's say, one end of the wire to another end of the wire. So what you usually do is you usually apply a potential, right? So once you apply a potential difference, this is the positive end, this is the negative end, because of which the electron will start flowing, and that is something which gives rise to the current, right? So this similar idea of potential is also applicable in vacuum technology, okay. So you have to understand that potential is not something which is only connected with electricity or electronics, okay. You need to understand these ideas are quite common, okay, and it is based on this that energy will actually have a direction of flow. So let's say, for example, this is a box, okay, and you have got stored some gases in this end, and there you don't have anything, right? And as soon as you make a slight opening here, okay, as soon as you make that slight opening, these molecules will start rushing, okay. So in general we can say that this is actually flowing from a region of higher potential, okay, to a region of lower potential, okay. And this will continue unless the potential at both the positions are same, okay. So now you understand that if I create a vacuum, that means we have got that particular system, okay, at a lower potential. And then if we can have that space, if we have any gas molecules on one side, or air molecules or water molecule, whatever, okay, these will rush to the other end because there is a difference of potential, okay. And based on this, what we have is nothing but the vacuum technology. For your purpose, most of the time this vacuum technology is something which you will be using in your lab classes, okay. For doing practicals also you need vacuum, okay. So vacuum has got greater effects. For example, you want to reduce the boiling point, okay, or you want to increase the boiling point, okay, you can actually create a pressure difference, and vacuum is all about pressure difference. If you reduce the pressure to a very minimum value, you are kind of creating a vacuum, okay. So we are going to learn about these things in this particular unit, okay. So in general this is a unit which is very much integral to the part of this syllabus, okay. We usually don't study that much about vacuum in detail in any of the syllabus, okay, in any of the subjects. So we are going to do that. So in general, when we define vacuum, it means something which is empty or void, okay. And if I say something is having a perfect vacuum, it's kind of very difficult to achieve, okay. Because if I say perfect vacuum, it means that we have a space with no solid, okay, liquid or gas, liquid or gas, okay, etc. I can write down, even I can consider some kind of plasma state, okay. So this is perfect vacuum. We don't have any solid substance there, no liquid or not even gas, okay. So we don't have anything there. That's what is called as perfect vacuum. And perfect vacuum is something which can be created as a man-made system, because in the universe, considering something as perfect vacuum is still not valid, okay. So that is there. So this perfect vacuum is basically something which is more or less theoretical, okay. It's not that you will be able to achieve a perfect vacuum and very very easily, okay. We can go to a very high vacuum but not perfect vacuum, okay. So practical to achieve, it's only theoretical, okay, and not practical, okay, to achieve perfect vacuum. We need to consider these points, keep in mind, okay. And then how do you define usually vacuum? It depends on what is the pressure inside a system, okay. So you have a closed enclosure, and you measure the pressure inside that enclosure. Based on this you will say what kind of vacuum it has, okay. Does it have a very rough vacuum, it has got a high vacuum, it has got an ultra high vacuum, and so on, okay. So this is something which we are going to cover in detail in this particular unit. Okay, so pressure in vacuum will basically be nothing but lower than atmospheric pressure. So since I'm talking about atmospheric pressure, and since this is the first class for this particular topic, so maybe we can just take some ideas, basic ideas here. Okay, so you have, let's say, at this particular point, you are basically having, let's say, the sea level. Okay, this is your sea level. Okay, now right now I'm in Nagaland and all of us in northeast, right? So we are not at sea level, we are somewhere above the sea level. Okay, and if we just go to the surface of the atmosphere, okay, we have the atmosphere somewhere here, it's covering us, right? We have the atmosphere somewhere here. So this atmosphere will have more pressure here because there is more space covered. So at sea level the pressure is going to be more. Okay, but since we are at a elevated level, because we are not at sea level, okay, right, we are northeast and most of the regions are above sea level. Okay, so specifically in places like Nagaland, Meghalaya, Mizoram, we are hill stations, so we basically are above sea level. So we have got less atmosphere above us, so that means the atmospheric pressure at this level is going to be less, and at sea level it's going to be more. Okay, so in general, when we consider this in case of vacuum, okay, it depends on what place we are in to actually measure the atmospheric pressure. So in general, if we say sea level, we say it's 76 millimeter of mercury. There is a very simple experiment to know this, okay, and this is something which I will discuss eventually. But you have to understand that if I am able to lower the pressure, okay, then I can say that we are actually in a vacuum system. So if you have a box at the sea level, it's under atmospheric pressure. So how do I lower the pressure inside the box? The idea is simple. What happens is, whatever air, gas, water, solvent, liquid, solid we have inside this box, we can just drag it out. And if we drag it out, the pressure inside this box will be lesser. Okay, so that means that the pressure on the box might be more, but within the box we are actually maintaining a vacuum, so we have dragged out all the elements out of it. Okay, so this is the idea that we have basically when we talk about pressure. Okay, so we have to remember the basics of atmospheric pressure, and that is very important. Okay, and then finally, how do you know that how much vacuum has been created? So this degree of vacuum is decided by a term which we call as the mean free path. So I hope you know about mean free path. So you might have a molecule, okay, and it might be colliding every now and then because we have got a lot of, let's say, a lot of particles within a system. Okay, now if it travels a larger distance without colliding, okay, understand this, if it travels a larger distance without colliding, that means it's going to have a larger mean free path. That means more vacuum. So if we have particles like this is one example, let's say, and let's say I'll take a box of similar size and we have got just these particles. So any particle here, the chances of it colliding would be more. It might collide here, it might collide here, it might collide here, and so on. But then when we consider this box which has got only two particles, it will collide at a larger distance. So less particle means more vacuum. So vacuum is more here, vacuum is less here. So that's how the mean free path lambda usually decides how much is the degree of vacuum. Okay. So having said about mean free path, I think we should just write down one definition for mean free path. Okay, and I think it's something which you have already studied. Okay, but anyway, we will just go around with this. Okay, the average distance, okay, just traveled by the molecules between subsequent collision, or you can write down even two consecutive collisions. Okay, subsequent collisions. That's how you actually define mean free path. Okay, so if the value of lambda is more, okay, means more vacuum, and this is the reason which I've just explained now. It's the same logic, means more vacuum. Okay, so that's how you actually understand mean free path. So you have to understand this. So if the value of lambda is more, the vacuum would definitely be more. Okay, but then this mean free path, or how the gas molecules within a system are going to behave, will depend on a number of factors. For example, you might say that there is temperature, so the vibration would be more, the collision would be more, and so on. Okay, so there are certain factors based on which it depends. It also depends on the pressure. So you're just going to write down one relation. We're not going to really derive it. Okay, but this is a relation which you might have seen before. This is mu divided by P. Okay, and then this is pi R. R is the molar gas constant, if you remember, divided by 2. Okay, and this is whole thing to the power half. Okay, so this mean free path will depend on these factors. Okay, and I think we can just make a basic idea of what are these terms. Okay, so mu is basically nothing but viscosity of gas. So any liquid, okay, anything which flows, any fluid, will basically have this viscous property. So viscosity of the gas, and that will definitely depend on how dense the gas is. Okay, P in general we can say is nothing but pressure of gas. Pressure of gas. So if you are considering an enclosure, we can study it in that aspect. Okay, and then we have got T. Okay, and that's nothing but temperature of gas. Okay, and then we have got R. Okay, so we call it as molar gas constant or specific gas constant, right? Specific gas constant. So you have to remember this relation in order to understand this particular topic better. Okay, so what does it mean? That if the mean free path is more, okay, that means the pressure must be less, because we are talking about vacuum technology. So we are going to talk in terms of pressure. So if the pressure is less, the mean free path is more, and if the pressure is less, means we are talking about more vacuum. By the way, we do have this common notion of making mistakes with the spelling of vacuum. It is VACUUM. Okay, it is not VACCUM. Sometimes we do make that mistake. Okay, and it also temperature dependent. If the mean free path is more, that means the temperature, okay, will also play a role. But anyway, we are not talking about temperature right now. Okay, we can just talk about pressure. So maybe not confuse you with temperature term. Yeah. So I'm just talking about simple words because we are going to talk more about pressure now. So mean free path, the pressure should be less. It comes from this relation, and it also comes from some logical understanding of the same. Okay, so this lambda, okay, it will actually decide the flow regime. Okay, it basically, let me write it down here, decides the flow regime in vacuum. Flow regime in vacuum. Okay, so if you just remember viscosity, okay, and if you remember this Stokes law, F is equal to
Sir,
6 pi, yeah.
sir, what is lambda? Lambda decides the flow.
Lambda is the mean free path in this case.
No, no, this line, lambda decides the flow.
Decides the flow regime, FLOWREGIME. I'll explain this
M.
now. Okay, REGIME. Okay, flow regime in vacuum. Okay, so if you come across this Stokes law, F is equal to 6 pi eta RV, and let's say you have got a pipe. Okay, this is something which you might have studied in your class 11, if I'm not wrong, and you have something like this, and you have got some flow of, let's say, water. Okay, and depending on a factor which we basically call as Reynolds number, okay, we can say whether this flow is turbulent or streamlined. Okay. Similarly, in case of gases, we can use this term lambda and decide the flow regime, and based on this we actually have got a number which decides this factor. So this is nothing but something which complements the Reynolds number in liquid flow. Okay, so this is something which we are going to analyze now. Okay, so let me take another page. Okay, so or maybe I can just move this off and do it here. It's not needed. This is just for explanation. Okay, hope you understand this. So similar to Reynolds number, we have got another explanation. Okay, based on which we can say that whether we are having a streamlined flow or a turbulent flow and so on. Okay, and that is basically called the Knudsen number. Okay, K is silent here, so Knudsen, Knudsen number. Okay, and this Knudsen number is usually denoted as n to the base kn. Okay, this is Knudsen number, and it is used to categorize. Okay, we are going to categorize the flow here. Categorize, okay, the flow regime. That means to which category does it belong? Is it a turbulent flow, streamlined flow? These are the regimes that we're talking about. Okay, flow regimes in vacuum. So in general, if I say this, I should mention this also. This is analogous to Reynolds number. Okay, so if we study Reynolds number, this idea is also not very difficult to grasp. Okay, Reynolds number in fluid mechanics. Reynolds number in fluid mechanics. Okay, so let me just write down a relation here. What happens is this Knudsen number, let me write it down as nkn. It can be written as lambda divided by d. Okay, and lambda is of course the mean free path. Okay, free path, and d, which is this capital D that we are talking about, is called the characteristic diameter. I'm going to explain this. Characteristic diameter. Okay, so this is your Knudsen number, which is actually complementary to the Reynolds number that we have. Okay, let's try to understand it a bit better. Okay, and try to actually draw some pictures out here. Okay, let me take one more page now. So what happens is this lambda is more, that means this nkn is going to be more, because if we just look into this relation of nkn is equal to lambda divided by d, it means that this will be more if lambda is more. So lambda more means there is more vacuum. So for a system where the vacuum is more, we can easily say that the Knudsen number is more. So if the Knudsen number is more, we say it's more vacuum. Okay, so it's the idea is that. So in general, if I just draw a line here, okay, and let me try to separate this out into three sections. Okay, so let me say this is your first section. Okay, let me just take it into three sections here. Maybe this is one section, maybe this is another section. Okay, and let me just try to write down some values. Okay, so let's say this is near about 0. Okay, and then this is 0.01. Okay, and then this is 0.3 and so on. This is not equally divided. Okay, I'm just giving you a basic scale here. Okay, so if this Knudsen number is here somewhere, okay, we can basically call it as continuum. Okay, TINUUM. Okay, this is continuum, And here we can basically call it as mixed flow. Mixed flow. Okay, and finally here it is free molecular. Okay, this region is called free molecular. Okay, so these are the three regions. Okay, so if you basically consider for Reynolds number, okay, for Reynolds number, we can actually divide it into three regions. Again, it has got this logic of continuum if the viscosity is too high. Okay, and then we have got it as streamlined, and then finally turbulent. Okay, so if we just to take out an analogy between these two, we can say it has got three regions: continuum, mixed flow, and molecular. For Reynolds number, it's continuum, streamlined, and turbulent. Okay, and this is how it works. So basically, if you look into this timeline, this means that mean free path will increase in this side, and the Reynolds number will also increase in this side. Okay, so that means in this particular region, let's say this is your region 3, region 2, okay, and then region 1, then out of these region 3 has got maximum vacuum. So if you remember Reynolds number, the values were somewhere like around, let's say, 1000 and so on. Okay, so it's a different unit altogether, different type of calculation. But in this particular case, if you have the value as 0.3 or greater, you're going to go towards a vacuum range. Okay, so more vacuum. So it's not that this is the end, we have got even more vacuum than this. Okay, so you can have a greater vacuum. Okay, so just as here, if the Reynolds number becomes very high, it becomes a turbulent flow. Okay, so turbulent flow means you are not going to really have a uniformity in the flow of the liquid. Okay, similarly here also you can have more and more vacuum. Okay, so that is there. So next what we have is nothing but the unit of pressure, and this is something which you already know. Okay, unit of pressure. Okay,
Hello, sir.
so yeah.
Sir, what is Knudsen number? I don't understand.
Okay, so let me just explain this Knudsen number again. Okay, so mean free path. What can be the possible unit of mean free path? We have more terms with this. Okay, so let's say the possible unit of mean free path is meter, and diameter, so maybe it's the diameter. Let's consider this as the diameter along which your gas is flowing. Okay, gas is flowing, so let's say this unit is also meter. So you have a ratio of meter by meter. That means this value that you are going to get, which is the Knudsen number, is basically a pure number. That's the first point. So that means it doesn't have any unit, it's just going to have a value. And as we can see from the graph here, okay, we can have a value of 0, that means it is continuum. We can have a value of 0.01, okay, or in between, or we can have a value of 0.3. So these are the values that it can usually take. Okay, so this diameter that we are talking about, okay, that's diameter. Let's say we have got a very small region, and then also the mean free path, okay, of the system. Okay, that means the time between, or how many collisions. Mean free path will actually give you an idea of how many collision an atom or a molecule will suffer, okay, between, let's say, a particular time frame. So let's say this time frame is there, and we already have measured lambda. Okay, but then how much collision it will have will depend on how thick or thin the region is. If it is in a very small closed enclosure, the chances are that this mean free path will be high. However, if there are less molecules, the chances are that this mean free path will be less. So if it is a larger enclosure, this D will be more. If it's a smaller enclosure, the D will be less. That means both lambda and D decides on how much is the vacuum, how many molecules are present, what is the mean free path. Both lambda and D are actually the factor. So what this equation does is considers both these factors, okay, and gives us a number which can help us to decide whether a system is high vacuum, low vacuum, no vacuum, or mixed vacuum. Okay, so this Knudsen number is nothing but a relation between the mean free path and the diameter or the space through which your gas molecule flows. Is it a bit more clear now, Pragyan?
Uh, Sir, is it
So
represent the
what we will
number
do,
of the
no, it doesn't represent the number of gas molecules. It just
it's
represents a number.
the number.
Do you recall Reynolds number in Stokes Law?
Sir, I forgot, sir.
Yeah,
Little bit.
yeah. So that, yeah, I know it's because it was in class 11, and this chapter is not put much attention. So I know that this Reynolds number is a bit confusing. What happens is that if you have a streamlined flow, that means you are going to have a flow which is going to be more or less uniform in nature. When it is turbulent flow, it's going to be non-uniform. Okay, there is going to be a lot of rush in the water flow, and this is actually decided by something which is called Reynolds number. Now this flow or whatever flow we are talking about will depend on a number of factors. Okay, so empirically it was observed that the factor on which it depends, if we consider all of them at the numerator and the denominator, the unit here and the unit here will remain the same. That means the final value or the equation that we have will be unitless. It will be unitless. So if it's a unitless, that means it's just a pure number. Since it was found out by Reynolds, so it is basically called as the Reynolds number. That's the idea here. So here also what
Understood.
happens is, you got it now? Yeah. So now what happens in Knudsen number also, Knudsen was a scientist who has actually given this idea that if we understand Reynolds number, we can understand Knudsen number also. Now this flow of gas molecule within a chamber, okay, will depend on how many gas molecules are present. Now let's say I want to create a vacuum. So that means I'm taking out the gas molecules. So as soon as I take out the gas molecules, what is the factor that is getting affected? It is getting affected by the mean free path. It is getting affected, it is affecting the mean free path. So that means we have got the mean free path. And we also see that how much region is there from which I have to take out the gas molecule, and that will be decided by the factor D. So that means this lambda and D are both connected. Okay, what does it mean? That if I say lambda by D, okay, we can simply say it as lambda is proportional to D. So that means if lambda is more, D should be more, or in the other words, if D is more, lambda should be more, right? Because if D is more, that means it is larger region, that means the mean free path will also be more. But on the other hand, if D is less, this lambda is also less. So lambda is proportional to D, that means lambda is equal to some constant into D, and this constant is nothing but the Knudsen number. I think this should be clear now, right? So we have to understand how does the system work in order to understand that the relations. Okay, so here lambda and D are directly dependent. Okay, so coming back to the pressure, we basically have the unit of pressure as Pascal, okay, or we usually write it down as Newton per meter square. Okay, if you remember from the basic definition of pressure, it is nothing but force per unit area, right? So it is Newton per meter square, and that is nothing but Pascal. Okay, we also denote it as bar. And if the pressure is too low, we're measuring it, we usually measure and go up to millibar. Okay, and since I talked about pressure, I think we should talk about a bit of standard atmospheric pressure also. Okay, standard atmospheric pressure. Okay, so
Sir,
standard atmospheric, yeah.
sir, then can you explain the graph which is continuum flow and molecular?
This one, this graph.
Yes, sir.
Yeah, so this is basically not a graph. This is just a scale to show you the representation of continuum state, mixed flow state, and molecular state. In other words, what I can do is I can write down the value of Knudsen number 0 to 0.01. So this is your Knudsen number, NKN. and then the second range might be 0.01 to 0.3, and the third range is 0.3 greater than 0.3. So the first range within this is called continuum. The second range is basically called as the mixed state, and the third one is basically called free molecular. So we really cannot call it as a graph, it's just a representation in a line. Okay, so that's there. So what usually happens is that, does it mean that as soon as I go from 0.01 to let's say 0.02, it will suddenly convert to mixed flow? That is not true. Okay, it is something like wavelength of light. Imagine you have got the visible range of light from 400 to 700 nanometer. Does it mean that as soon as it goes to 701 it vanishes? I directly jump into the IR region? The answer is no. When I go to 700 1 nanometer, the visible range, that means at 700 nanometer, let's say it is the red light, okay, it's the other end. So it's the red light. The red light will slowly start to diminish, okay, and as I go to higher and higher values, this red light will slowly vanish, and we will have more of IR radiation. So it is moving towards IR. So here also, as soon as it crosses this 0.01 line, that means it is moving towards the mixed flow. It does not become mixed flow totally, it's moving towards mixed flow. So maybe somewhere in the middle, let's say around, let's say 0.2, this will be totally mixed flow. It won't have any component of continuum, it won't have any component of free molecular. But as it approaches very close to 0.3, let's say it is 0.29 or 0.2627, that means it will both have a mixed flow as well as some component of free molecular flow. Okay, now what does it mean? In simple words, free molecular means the mean free path will be more. That's means free molecular. If the mean free path is less, okay, and bit constrained, we basically call it mixed flow. And if it is very much constrained, that means within millisecond, microsecond, it is colliding. That means we have got too many gas molecules into the system, and we basically call it as continuum. So in general, continuum means we have got a continuous system. Okay, we do have a continuous gas molecule present in the system, because of which we cannot say that the mean free path is high. The mean free path will be very less. Okay, and that is the basic difference. Okay. Okay. So coming back to this standard atmospheric pressure. So if I talk about standard atmospheric pressure, there are different ways of writing it down. Let me just write down few of the values which you might have come across. Okay, 0.1013, okay, into 10 to the power 5 Pascal. Okay, that's there. Okay, or Newton per meter square. So the SI unit is Pascal, which is nothing but Newton per meter square, which is because it is force per unit area. Okay, so this is very basic. I in fact should not teach you this, but I think you can recall this once. 1 bar, this is equal to 1 bar. So 1 bar, if you convert it into Newton per meter square, it will be 1.013 into 10 to the power 5 Pascal. Please remember these conversions. What happens is, in entrance exam and all nowadays, they are obviously providing the value. So this value might also be provided, but the conversion you must know. So 1 bar is 1.013 into 10 to the power 5 Pascal, and accordingly you can do it in millipascal, megapascal, and so on. Okay, but then if I want to convert it into atmospheric pressure, it is nothing but 760, sorry, I wrote 76 before, that was wrong. 760 millimeter of mercury coulomb. I will explain you what it exactly means. Okay, you might have read a lot of sentences on this. Okay, at standard sea level, standard sea level. Okay, so maybe I can just rub some things here. Okay, so this is what's pressure is all about, and this is what we are talking about here is standard atmospheric pressure. 760 millimeter of mercury coulomb at standard scale, okay, or standard sea level. Okay, level, yeah. So what does it mean? So let's say I have got a bucket of mercury This is mercury, and I have taken it at the sea level. This is at sea level, okay. So that means above this bucket of mercury, the atmosphere is giving out some pressure, and then within this I can place a very thin capillary tube, okay, and then I can graduate it and mark the scales, 10 mm, 20 mm, 30 mm, 40 mm, and so on, okay, and go up to 1000 millimeter. So it's a capillary tube. So if there is mercury here, because of the pressure that atmosphere exerts on it, this mercury, and it will rise in the capillary tube. You can see this demonstration in YouTube also, okay, and it will rise up to a level of 760 millimeter, and this is how we say that it is 760 millimeter of mercury coulomb at sea level, okay, standard sea level, okay. So this is how atmospheric pressure is usually measured, okay. So if you have any kind of analog device in your room, okay, or a digital device in your room which measures pressure, okay, the idea is this: how much of the atmosphere you have above you, and that pressure is being measured here, okay. So if the measurement is done based on, let's say, Newton per meter square and so on, okay, you can easily convert it into this scale by knowing this conversion, okay, or you can convert it into any other scale, let's say if you are not at the sea level, okay. So it's 760 millimeter of mercury at sea level. It will be lesser at whatever atmosphere we are at right now, so maybe in Assam, or maybe in Nagaland, or Mizoram, Meghalaya, okay. This will be definitely less, this won't be more, okay, this will be less. So this is what is atmospheric pressure is all about, okay. But then, if I talk about vacuum, will this pressure unit be enough? Because in vacuum, what happens is the pressure falls down further, okay, the pressure degrades further. How do I measure that? So there are other units of vacuum as well, and I think we can measure this, okay. In vacuum, other units of pressure, okay, unit is torr. There is a unit which we basically call it as torr, okay, and torr is nothing but a representation of millibar. So bar, you already know, 1.013 to 10 to the power 5 Newton per meter square, 1 bar, and you can convert it accordingly, and you can get it in millibar. Okay, so because millibar is nothing but considered as, okay, it's better, okay, it's much more less, okay, compared to the standard atmospheric pressure that we have, okay. So this was actually, this Italian scientist, okay. Yeah, I hope I can pronounce it correctly. Evangelista Torricelli, okay, that was named as right. Sorry, okay, Italy, okay, in 1644. So this concept of vacuum pressure and all is quite old, okay. And if I just measure this, 1 torr, okay, is equal to nothing but 1 millimeter of mercury, okay, at standard sea level. So this is usually considered this, okay, this is graduated in such a way, okay, standard sea level. And maybe I can just write down this one more: 1 torr is equal to 133.28. Since we are talking about vacuum, we need to know all these conversion. That's very important, okay. 0.28 Newton per meter square, right? So that's about pressure, okay, that is important here, Newton per meter square. So there is so many things to learn. Maybe we already know about these things, but sometimes we miss out on these important concepts, okay, and later on we realize that although we have studied this, but we don't remember. So that's why I made it a point that at the beginning of this unit I give you all the basics first, and probably we can just proceed from there, okay. So it is expected that you know these things. There is no harm in revising it properly. Conversion table, okay. So let me just give you a very simple conversion table. What we are going to do here is we are just going to have a conversion table which you probably can write it down in your copy and paste it in front of your study desk so that you remember it, okay. So we do have the units as Pascal, okay, and then we have got bar, we have seen, okay, then we have also seen atmosphere, okay, and then we have finally seen torr. So I will probably just try to make out a table for you, okay. So Pascal, and then bar, atmosphere, and torr, okay. Don't concentrate on the slanting of the line, not good obviously. So the first might be 1 Pascal, okay. This is a good way to represent it, okay. I got it somewhere, so I thought, okay, I'll just share this with you. It looks okay for me. Good way to remember. 1 atmosphere and then 1 torr, okay. And this side also we can convert it into Pascal. That means 1 Pascal, and this is equal to how many Pascal? So the 1 Pascal will be 1 Pascal obviously. Then we have got the conversion as bar, and then we can actually write it down in atmosphere, and then we can actually write it down in torr, okay. So whatever I have told you here, it's actually the same, okay. So if we just go back to the previous page, if you look into here, 760 millimeter of mercury column at standard sea level. So this is a measure of atmospheric pressure. So 1 bar is also a measure of atmospheric pressure, okay. So when we talk about atmosphere, we are more or less talking about this particular factor, okay. So I'm just giving you this table, maybe you can just read it once, okay. So 1 Pascal will remain as 1 Pascal, we know, but 1 Pascal is equal to how many bar? So if you do the conversion, 10 to the power minus 5, you can just cross check it once with whatever values I've given, but I hope this is correct. If you write it down in atmosphere, it is 9.8 into 10 to the power minus 6 atmosphere, okay. And then this is 7.5 into 10 to the power minus 3. In fact, you can try and do this table on your own after doing some calculation, okay. So 1 bar is obviously equal to 10 to the power 5, you know, bar. 1 Pascal is 10 to the power minus 5 bar. So 1 bar is 1 divided by 10 to the power minus 5. So that becomes 10 to the power 5, right? So it's so simple. This will remain as 1, obviously, okay. And then this will become 0.98. Once you have this first part, the second one should not be difficult, okay. Usually this is helpful when you want to do your calculations fast and don't want to get stuck with conversions, okay. Maybe 10 to the power 5, 1.013, okay. You can do the calculations. This is 1, okay, and this is 760. That's it, okay. So next what we do is 1 torr. So 1 torr is 133.3, okay, to Pascal, torr to Pascal. This is 133 into 10 to the power minus 3, okay, and then this is 1.31 into 10 to the power minus 3. This is 1, okay. So now you understand this, right? So if someone tells you that there is an atmospheric pressure of 1, there is 1 atmospheric pressure, you can straight away say it's 760 millimeter of mercury, okay? Or you can say 1.013 into 10 to the power 5 Pascal or Newton per meter square, okay? Whichever is comfortable for you. So I want to make these things absolutely clear, because you know, after you finish your MSc, probably if you're working in some lab and doing some experimental physics, okay, you need to know these conversions and units, okay. These are also some of the questions which might be asked, okay. There are certain techniques for synthesizing nanomaterial like chemical vapor deposition, physical vapor deposition, and so on. There are a lot of vacuum technologies used, okay. So there you need to convert from one unit to another. So probably if you keep your notes properly, these might be very much useful to you, okay. So degree of vacuum, the next topic is degree of vacuum, okay. So what do I exactly mean by degree of vacuum? It means that from what vacuum to what vacuum, so that means from what pressure, sorry, not vacuum, from what pressure to what pressure, what is the degree of vacuum that I usually call it with, okay. So this is what we are going to say. So on this side I will write down probably the degree of vacuum, okay, and on this side I am going to mention the pressure. What should be the range of pressure? So this is one more table. and rather than writing so many sentences, I prefer writing down tables here. Okay, so there are different vacuums. Okay, I hope I can cover it in this page. Okay, so let me just write down one by one. Okay, the first one is, we will call it as rough vacuum. So you know the vacuum is not very high, and let me call it as rough vacuum. That's the first part. Okay, the second one I will call it as medium vacuum. Third one, high vacuum. Fourth one is very high vacuum. Okay, and finally we call it as ultra high vacuum. So these are certain vacuum ranges that we have. Okay, and let's try to write down some values for them. Okay, under what pressure we have that. So I will need some space to write it, so I'll just make the table this way. Okay, so you know, for rough vacuum I will just write down it in different units. So let me write it down first. It may be between 250 torr, okay, the pressure, and 760 torr. So if we have the pressure between these two range, we usually call it as a rough vacuum. Okay, a rough vacuum. Or in general, if I just write it down in kilopascal, which is actually a very popular unit, Pascal, 3 kilopascal, and if you do the conversion, this is 103 kilopascal. That's usually the range of rough vacuum. I would suggest all of you to please make a note of this, okay, and keep it with you handy. Okay, you need it. And I do have this habit of asking you questions from the values that I usually give, so the chances are there that even may ask you this. This is 0.001 torr, the pressure, and 25 torr. Okay, in kilopascal, on pascal we can just say it is 0.1 pascal to 3000 pascal. Can be considered as medium vacuum. So you see here, this is pascal. Okay, this is kilopascal. So the pressure has reduced from 3 kilopascal, that means 3000 pascal, to 0.1 pascal. This is 103 kilopascal, that means already 10 to the power 5 you can say, and this is nothing but 10 to the power 3. So it is reduced. Okay, that is nothing but called the medium vacuum. So please note this range that we are talking about. Okay, okay, to 10 to the power minus 3 torr. Okay, on the other hand, if you just want to convert it into pascal, it is 0.1. This is millipascal now. So you see the pressure is slowly reducing. Okay, and 100 millipascal. Okay, so that's it for high vacuum. If you go to very high vacuum, it is 10 to the power minus 9 torr. Okay, you can just complete the table now, and this is 10 to the power minus 6 torr. So what happens is that there is a very fine line. This is 10 to the power minus 6, and as soon as it starts going lower than that, you are moving towards very high vacuum. Okay, and if you want to go to these such ranges of vacuum, you definitely need to have devices. Okay, so if you are having a greater vacuum system, you need to have a device which will actually cost you more. And if you have greater vacuum, probably your setup or experimental setup or whatever task you have based on vacuum will be better, but for that it actually will come at a cost. Higher the vacuum, more is the cost for the setup. Okay, this is 100 pascal. Okay, and finally this is, I think, quite obvious, this should be less than 10 to the power minus 9 torr. So what we are going to see eventually is that we are going to create this vacuum, what kind of device we will be using. If you want to create this, what is the device? and these two. Ultra high vacuum can also be created, but roughly these four types of vacuums are there which are more commonly used. So if you consider something, a normal pump which is connected in your home, okay, to raise the water from the ground level to the tank which is the top of the building, these are usually nothing but working on this rough vacuum system. Okay, sometimes it goes to medium vacuum, depends on how much you spend. So if you take a vacuum and if it costs you more, that means it has got more capacity, okay, of creating greater pressure difference. So when we talk about something like a vacuum cleaner, that also comes in different ranges, okay. So these are some of the criteria based on which the price can be decided.